Hello everyone, and welcome to our physics problem-solving session. Today, we're tackling a fascinating problem about sound, specifically how sound intensity changes with distance from its source. Understanding this is crucial for fields like acoustics, environmental noise control, and even communication. Our problem states, a barking dog delivers 1 milliwatt of power. If this power is uniformly distributed in all directions, what is the sound intensity level at a distance of 5 meters? Let's begin by visualizing this. Imagine our barking dog as a tiny point source at the very center. The sound energy spreads out equally in all directions, forming an expanding sphere. We are interested in the sound intensity at a point 5 meters away from the dog, which would be on the surface of this imaginary sphere. Now, let's identify our key variables and constants. The power emitted by the dog, denoted by P, is 1 milliwatt. The distance from the dog, R, is 5 meters. We need to find the sound intensity level, which we'll call beta, often measured in decibels. We also need a standard reference for sound intensity. This is the threshold of human hearing, I0, which is a constant value of 10 to the power of minus 12 watts per square meter. The relevant equations and principles are straightforward. First, sound intensity, I, is defined as the power distributed over a certain area. Since the sound is spreading spherically from a point source, that area is the surface area of a sphere, which is 4 pi r squared. So our first equation is I equals P over 4 pi r squared. Once we have the intensity in watts per square meter, we can convert it to the more commonly used sound intensity level, beta, measured in decibels. The formula for beta is beta equals 10 times log n to the power of I over I0. Let's substitute our known values and calculate. First, convert the power from milliwatts to watts. 1 milliwatt or 0.001 watts. Now, calculate the sound intensity I equals 0.001 watts over 4 times pi square meters. This calculation gives us approximately 3.18 times 10 to the power of minus 6 watts per square meter. Next, we calculate the sound intensity level, beta. Beta equals 10 times log n to the 3.18 times 10 to the minus 6 watts per square meter. 10 to the minus 12 watts per square meter. Calculating this gives us approximately 65 decibels. To check our answer, let's consider the units: power in watts, distance in meters, which correctly leads to intensity in watts per square meter, and finally decibels, which is a dimensionless ratio, as expected. A sound level of 65 decibels for a barking dog at 5 meters is quite reasonable. It's certainly audible, but not painfully loud. This confirms our calculation seems accurate. So, the sound intensity level at 5 meters from this barking dog is 65 decibels. This value gives us a clear measure of how loud the sound would be perceived at that specific distance. This problem beautifully illustrates the inverse square law, a fundamental principle in physics. It shows that the intensity of something spreading out from a point source, whether it's sound, light, or gravity, decreases rapidly with the square of the distance. The further you are, the weaker the effect becomes. The use of the decibel scale is also a key takeaway. It's a logarithmic scale that allows us to represent a vast range of sound intensities, from the faintest whisper to the loudest roar, in a manageable way, mirroring how our ears perceive sound. In summary, we successfully determined the sound intensity level by first calculating how the dog's power spread out over a spherical area, and then converting that intensity into the more perceptually relevant decibel scale. This approach is applicable to understanding how sound behaves in various real-world scenarios, from designing concert halls to mitigating urban noise pollution. Thank you for joining this session. If you found this explanation helpful, please consider liking this video, subscribing to our channel for more physics and math insights, and sharing it with your friends. And of course, feel free to leave any questions or comments below. If you have a specific physics or mathematics problem you'd like to see solved in a future video, you can support our channel by making a donation. Each month, we'll select a few problems submitted by our donors and create dedicated videos to walk through their solutions.